Hey. Yeah. Yeah, no, we do. Yeah. So, guys, we're going to do something today that we will never do again. But I think you're going to find that you'll agree with me that what we are about to do is appropriate given the material. What you're going to find in this class is that many times the way that I break up the units in the class doesn't necessarily fall in line with the way Eugene wrote the book. And I call him Eugene because this guy right here, Eugene LeMay, he's actually a chemistry education professor at the University of Nevada, Reno. And back in the year 1999, I was going to be one of his PhD students. In 99, I decided that I was ready for a change, and I actually went out and met with Eugene, who's a wonderful person. And Eugene said, hey, why don't you come out and get your PhD in Chem Ed, and I'd love to be your advisor. And an amazing guy, and I was all set to go chill with Eugene for the next 5 years of my life. And I knew change was coming, and then it turns out the change was not hanging out with Eugene, because about a month later I met the woman that would become my wife, and it turned out that the change was not chilling with Eugene, it turned out to be chilling with Carla, and we decided not to move to Nevada and me get my PhD. Anyway, all of that to say, this is Eugene. So guys, open up Eugene's little thingy here to chapter 3. And what you're going to find is that, again, we are not always going to chunk this material the same way that Eugene chunks it. And understand he has co-authors as well. But guys, the other thing we're going to do is we're not going to necessarily go in the order that Eugene puts this material. For example, the next unit that we're going to do will be chapters 5 and 19. But the unit that we are about to engage in will be chapters 3 and 4. So really quickly, chapter 3, what's the title? Stoichiometry. Now go look at chapter 4. What's chapter 4? Yeah, what kind of reactions? Aqueous reactions. So guys, what does it mean if something is aqueous? It is in water. And if you allow your eye to scan through, you don't need to, but if you allowed your eye to scan through chapter 4, you would find out quickly that it's sort of a fundamental introduction to water-based chemistry. And then it gets more specific. It talks about precipitation reactions, it talks about acid-base reactions, and then it talks about oxidation-reduction reactions. Guys, what you're going to find out is essentially what we're going to do with chapter 4 is we are going to spend a big day on precipitation reactions. You remember that's all about solubility rules. That's why you memorize the solubility rules. Then we're going to do a day on acid and base chemistry. We did that last year. We're going to do a little bit deeper now. But understand, guys, the only reason we're doing acid-base chemistry is to allow us to talk about it generically until we get to March, and then we're going to spend 5 weeks on acid-base chemistry. Okay? Then, guess what the last unit of the year is going to be? Oxidation reduction chemistry. It's chapter 20 in the book, and it's going to be about a 4 or 5 day unit. So guys, really chapter 4 is a broad overview of water-based chemistry, and then it's the last quarter of the year. So how does that then tie into chapter 3? We'll go back to chapter 3. What is stoichiometry? Do you remember? It's the math of chemistry. Right. So guys, well, not everything. I got to be careful. Not everything. Most of chapter 3 you have already been introduced to, and you've done the homework assignment over the summer. Moles are up there somewhere in your head swimming around. You kind of have a general idea of chapter 3. So here's what we're going to do. We are going to do chapter 3 in order today. We're going to do all of chapter 3 right now. We will never do this again. But guys, what we're going to do is we are literally going to page through chapter 3, and we're going to go, remember this, remember this, remember this. We'll talk about some of the things that we really didn't touch on in great depth last year. But guys, the bottom line is we are literally going to do chapter 3 from front to back right now. And we're not going to do class like this ever again. Understand, we're not establishing a precedent. When we get into chapter 4 on Friday, we are not going to touch our books.
And for the last page, that starts with T through.
You'll have a little bit of time at the end of class if you haven't got your pictures yet, or you can go during Pride. We do have Pride today. We've got a couple things we need to do, and then you can go. So guys, again, chapter 3, which we're doing now, is going to be very reflexive. I'm just going to put the unit or the subunit headings up here on the board, and we're going to go, hey, you remember how to balance reactions? Great, let's not talk about it. But if I throw balancing reactions up here, and you're thinking to yourself, gosh, maybe I need a little refresher. Guys, please don't hesitate to say that. I'm willing to spend as much time as you want going back over and reviewing some of these things if that would be helpful. Sometimes I'll just remind you of the problem-solving processes. But guys, we're just going to rock it through chapter 3. You guys ready to go? Okay, so guys, looking at your books, so chapter 3, as you flip over to 3.1, is all about chemical equations. So guys, it's not just chemical equations. The idea is balancing chemical equations. Do we need to talk about it? Do you remember how this goes? Maybe we should talk about this. Why do we balance chemical equations? Law of conservation of mass, right? Everything that goes in has got to come out. So every atom that goes into a reaction has got to come out of a reaction. And many times in their unbalanced forms, that is not the case. And so guys, when we write balanced equations, when we balance equations, what we're doing is we're trying to validate the law of, or we're trying to respect the law of conservation of mass. So guys, when you're balancing equations, do you remember the tricks that I gave you last year that make this easier? What were some of the tricks that we talked about? Balance oxygens last. Guys, did you notice that a lot of the polyatomics that you memorized contain oxygen, nitrate, sulfate, oxalate? There's oxygens everywhere. You try to balance oxygens and you're just going to dig yourself a pit. So balance the oxygens last. What are other tricks that you learned? We'll talk about that when we start doing oxidation reduction, not start with carbon. What about polyatomics? Do you remember the rule of polyatomics? Keep them together if you can. When you're balancing equations, like for example, if you have something like this, so if you have sodium nitrate, and if sodium nitrate is reacting with calcium sulfate, and when these react together, one of your products is calcium nitrate, but calcium nitrate is this because calcium's +2, and then your other product is sodium sulfate. When you do this, you have the opportunity to not just balance the nitrogens, but you can balance the nitrates because they stay intact. Does that sound familiar to you? But remember, if we have a reaction like this, where sodium nitrate decomposes, and it actually decomposes into sodium nitrite, and that releases oxygen, now can we balance the nitrates? We can't, because the nitrate turns into nitrite, and because the oxidation, well, I can't say that to you, because the polyatomic changes form, you can't balance NO3 with NO2. So then you've got to balance it the brute force method. Do you remember that? I don't know. It doesn't matter. We'll figure it out later. So guys, what else do you remember in terms of tricks for balancing equations? Remember the odd, bless you, the odd even thing? Remember that? Remember, if you get to the point where you've got an odd number of atoms on one side and an even number of atoms on the other side and you can't get them to balance, what do? Double the odd number and then start over. You remember that one? That might be worth writing down if you don't remember that. And then, guys, finally, what do you do when all else fails? You're 10 minutes into this. You can't get the bugger to balance. Well, not 10 minutes, but what do? Brute force that thing. Yeah, you throw a 1 right here and see if it balances. And if it doesn't, you erase everything and you come back and you stick a 2 there. And you just brute force this thing until it finally balances. So there you have it. Those are my little reminders relative to balancing chemical equations. Anything y'all want to go over? You okay? You will in homework. Yeah. You guys okay? All right. So guys, let's take a look then at number 2. They call this patterns of reactivity. Where does it start? Some simple patterns of reactivity. But guys, if you page through the subsequent pages, what are they really talking about? Exactly. Guys, this is reaction types. Combination, which we call synthesis. Decomposition, which we call decomposition. Combustion reactions. What's missing from that list that you learned last year? Single and double displacement. And you'll find out, we'll pick those up in a minute. But guys, we've got synthesis, decomposition, combustion reactions, anything that you want to talk, and I think they're in my, there they are. Any of those that you want to talk about. What about general forms? Would that be helpful to you? Do you want to, we can do that quickly if you'd like. So guys, remember a combustion reaction is some hydrocarbon CXHX. It should be CXHY because those are seldom the same numbers. But it's a reaction with oxygen and your products are always carbon dioxide and water every single time. And then balance it. Yep. Always balance it. Yep. And then, guys, synthesis, you have some element or compound A plus some element or compound B. And really, technically, this could just go on and on and on. So this could be a string of things. But then the product of that is some C. The idea with synthesis is you always get one product. And then, guys, decomposition, of course, is the inverse of synthesis, where C breaks into A and B. Wait until we look at the energetics of those processes when we get into chapter 5. It's going to blow your mind. Okay, so how are we doing on this reaction type stuff? You okay? Is it coming back to you? All right. So let me clean up this mess and let's go on to 3.3, atomic weight. So guys, grab a periodic table, whether it's the good one or whether it's the one that you get to use. And guys, let's remind ourselves about atomic, or as it says in the book, formula weights. So if you've got our good periodic table, they are the numbers in the upper right-hand corner in red. If you've got the periodic table that you get to use on the test, where are they? The bottom of the box? Bottom of the box? Bottom of the box. So guys, when you have the atomic weight of an element, like for example, if you look at carbon, it's 12.01. What on stinking earth does that number tell you about carbon, 12.01? It's okay, first good, it's an average. And that's why they aren't whole numbers. So guys, let's back that up. Why would we expect the masses of these atoms to be whole numbers? Go ahead. Good. So do you remember the name of that unit? The atomic mass unit, yeah. So guys, all of these masses on the periodic table are in the units, atomic mass units. And that's not just the mass of a proton, it's also the mass of a neutron, because protons and neutrons both weigh 1 atomic mass unit. So when you see that carbon has a mass of 12, what do you now know about carbon in terms of its nuclear structure? 12. Not yet. You know 12 what? total protons and neutrons. So guys, the atomic number, the atomic mass tells you the number of protons and neutrons. Now I know that you understand this, that if you want to know what it's really made of, the atomic number tells you protons and then the remainder are neutrons, right? And I know that you understand that. But guys, fundamentally, these masses are the numbers of protons and neutrons. Now, why would we expect those numbers to be whole numbers? Because you can't have fractions of a proton and fractions of a neutron. So a proton weighs 1, a neutron weighs 1, you add up a bunch of ones, you get whole numbers. So now, Mark, come back to your thought. Why are these masses then not whole numbers? Yes, they are averages of all of the isotopes that exist. Now guys, remind yourselves, what is an isotope of an element? Different numbers of neutrons. And guys, I know you understand this, but let's be clear. There is not one proper isotope of an element, and then all the rest of them are mutants. So if you find a sample of carbon, it will contain carbon 11, carbon 12, and carbon 14. All of those are carbon atoms, but because they don't exist in equal ratios, the average of those works out to be 12.01. So these masses, these average atomic masses, are the averages of all the isotopes that exist. Is that all coming back to you? Okay, so fundamentally you need to get the idea that these are not whole numbers because we have multiple different isotopes that exist, and then we talk about average atomic weights, which is actually what these things are. Yeah?
When they were all solving and figuring out what the atomic numbers were for each of the elements, how did they actually figure out how many isotopes there were and how much of those isotopes actually existed?
Yeah, so we actually made this an extra credit project last year. So guys, the question on the table, and we can talk about it briefly, the question on the table is how do they come up with these numbers? And they do it through a process called mass spectroscopy. It's brilliant chemistry. Basically, the analogy is this. Imagine that I had a bucket full of balls. Okay, so this is an element called ball. Okay? But it turns out that there's two different isotopes of ball. One of these, well, it's not a great analogy, but follow along. One of them is actually volleyballs. The other one is bowling balls, okay? But they're all balls. It's just that some balls weigh more than other balls because bowling balls weigh more than volleyballs, right? Okay, but you get the idea. Now, what can we do to figure out the average mass of all of these balls? Well, obviously, we could just put them on a scale and weigh them and then count how many of them there are and figure out the weighted average, right? But you can't do that with atoms. So what do? And the answer is you throw them. So this is the analogy. Imagine that I had a catapult, okay? And I cock this catapult back and I stick a ball. I don't know if it's a volleyball or a bowling ball, but I stick the ball in the catapult and I throw it. And if I keep doing that, and if I keep throwing all of the balls in the bucket, eventually what's going to be out here in the room? Two piles of balls. Which balls are going to be right here? The bowling balls, and of course the volleyballs are going to be out here, right? Why did the volleyballs go further? Because they're lighter. And guys, that's actually what they do with elements, with atoms, to figure out their average atomic mass. They heat them up really hot and turn them into a gas. Then they ionize them by hitting them with radiation. Now they have a charge. Then they take that ionized stream of gas and they pass it through a magnetic field, and that magnetic field throws the atoms. And they know how much energy they're putting into these atoms. And the heavy ones land here, and the lighter ones land out there. Now, how do they collect the data? Well, what they do is they measure the distance that the atoms flew. And by knowing that distance, and by knowing the amount of energy that they put in the form of the magnets, they can figure out how much these weigh. The math is pretty easy. So they figure out how much they weigh by the distance that they flew, and then they can count the number of atoms that land in each pile with the detector, and that's how they figure out the average atomic mass.
How do they actually harvest the actual amount of atoms that they want to use?
It doesn't matter how many you use. You just need to know a ratio. You could use 10 or you could use 1 billion, and it doesn't matter. Yeah, because the ratios are the same. So guys, do you remember how to analyze that math once you're done? Do you remember the equation? Maybe we should write it down. So guys, it goes like this. Average atomic mass is equal to, do you remember sexy E? Remember that guy? And it's mass times abundance, and all of that is divided by 100 to turn it into a to a percentage.
The abundance would be a percentage.
The abundances would be percentages, and then the masses are the masses of the elements. Yep. So guys, let's take a peek here really quickly. Where are we at? Where did it go?
Sorry, could you say what is that, the actual Greek letter mean again?
It's sigma, which stands for sum.
Oh, okay, so the sum of the mass.
Huh. This is interesting. Where did this go? Where are we at? So formula weights. Oh, wait a second. No? Okay. We're okay. All right. So guys, is that all coming back to you? You're okay? Okay. So guys, let's do this then. Let's continue on. So we just got done with 3.3 with formula weights. Let's go back to 3.4. Oh, hold on. I got to clean this up. And then I got to do this. And here we go. Do you remember this mystical, magical day? The day where your life changed forever. You met the mole. Yeah.
So I just got a question about my calculation people. It's got the mass. It has the mass proton and neutron in there.
Yeah.
They're different by like 0.001%.
They are. The same way. They just propel them with magnetic fields and measure how far they go. So, yeah. Hey guys, let's talk about this really quickly. So, this is something that we need to work on as a group. Understand that I'm in no way, you just need to understand this. So guys, and understand I have this conversation with every AP class that I've got, and we need to talk right now, and the conversation goes like this. And I know you guys are gonna understand this because you're bright. Okay, so the idea is this. We have a very clear sense of what we need to accomplish today, right? And it's because I set that out for you. Now, that means that what I've done by setting the vision for the day, for the class, is that I have now implanted in each and every one of you a filter. And here's how that filter functions. See, guys, and understand that for some of you, this filter is going to hit overload. And that's good because, guys, you are bright, inquisitive, curious people that are going, wait, I've got 11 questions about what we're talking about right now. Now, guys, here's the one of the 11 million drawbacks to public education. See, guys, I've got a job. My job is to get 26 of you from point A to point B. And the problem is if we run down all these really interesting rat trails, we're going to end up over here, and some of you are going to be getting your needs met, but we're not going to make it over to where we need to be as a group. So here's what I'm going to ask, and I know that you guys are going to understand this, but please, guys, before you ask questions, you need to ask yourself this question. Does this benefit me, or does this benefit the group? Do you understand what I'm saying? And if the answer to that question is, I really think that we are all going to benefit from the answer to this question, ask. But guys, if you think that question and you're like, yeah, you know, this is just sort of something I'm interested in, that doesn't devalue the question. What it does is it means that you've got to address those questions in a different context. Do you understand what I'm saying? So guys, please understand, I'm not in any way trying to squelch your curiosity. What I am trying to do is I'm trying to make us into a high-functioning group rather than a bunch of curious individuals. Does that make sense? Okay, so guys, with that said, let's talk about the mole. Now guys, the bottom line is this. When we talk about this idea of the mole, you understand that there's a lot to this, right? So first of all, let's have this conversation. What's the mass of carbon? 12. 12 what? Atomic mass units. What does that tell us about carbon? 12 protons and neutrons. But then, guys, you had this magic aha moment. You found out that one atom of carbon weighs approximately 12 AMUs. And you realize that that number is so ridiculously small that it's worthless to us. We obviously don't have a balance that measures in AMUs, and that doesn't do us a bit of stinking good, and our periodic tables are broken, and we may as well burn them in a pile because that data is no good to us because functionally we can't measure AMUs. And then you had this magic moment where you figured out that if you can't weigh one carbon atom because it doesn't weigh enough, what do you need to do? Get more carbon atoms. And then if you had me as a teacher, we played this stupid game where we said, what if we got a dozen? That's 12. It's not heavy enough. What if we get a gross? That's 144. It's not heavy enough. And then we said, how many atoms do we need so that we finally have a big enough pile that we can weigh it? And we found out that the answer to that question was this ridiculously large number, which is named after the dude that came up with it, whose name is Avogadro. And just like 12 is a dozen, and just like 144 is a gross, 602 septillion is a mole. And when you have a mole of things, you finally have a pile of things that is big enough that you can weigh it. And it turns out that if you have a mole of carbon atoms, it also weighs 12. But it's no longer 12 AMUs. It is now 12 grams. And you found out that Avogadro's number was the number of things you need to have a pile of things that has the same mass in grams as one of these weighs in AMUs. How was that for a good review? Not bad? Now guys, could you imagine learning that in college for the first time? Because the time that I just spent on that, re-explaining it to you, is how much time they spend on it in college, even if you've never taken chemistry before. And the expectation is not only did you understand what I just said, but you can also use that number computationally. You're not going to like college chemistry. You understand that's why you're taking this class from me, to make that easier. So guys, any questions about the concept of the mole or atomic masses in grams? You're good? Okay. Oh, go ahead. Good question. Grab your period. Grab this thing. So if you go over here, there it is. So on the page 3 side, down here, you'll notice that this table where the constants are on the right and the equations are on the left, they give you 6.022 times 10 to the 23rd. So that is the number that they will use on the AP test to determine significant digits many times. So they'll be looking for 4 potentially significant digits. Understand that most of the time when I do my answer sets for the homework, I'll just use 3, 6.02. So either one's fine. But understand on the test, they'll prefer you use that one. Okay, so guys, really, and I know you understand this, but the bottom line is that this is really stuff you need to just figure out on your own. So we're gonna go on. It's not like we could spend some time and actually help you. You just need to go back and do some problems. And we'll actually do one in a minute, but we're gonna save it for a minute. Okay, so now guys, I have skipped forward to empirical formulas. So let's make sure we remember what empirical formula. Do you remember what empirical formulas are? It's the simplest formula for a compound. And so guys, when we talk about empirical formulas, let's do this quickly, because this is a word that we're going to use a lot in this class. The word empirical. Guys, do you know what it means to have empirical evidence? It's not just a chemistry term, it's a legal term. The word empirical means something. Do you know what it means? No, it means based on experimentation. So guys, when you have empirical evidence, it is not evidence that is brought by somebody testifying. Empirical evidence is like DNA evidence in a courtroom. It's something that's based upon experimentation. So when we talk about empirical formulas, we are talking about formulas that are based upon experimentation. Now guys, for us, that really means simplest formulas, but understand it really has a broader meaning. So how do we come up with empirical formulas? And guys, the answer is, and I'll explain it to you in a minute how they do this, but guys, what they do is they simply tell us the relative number of atoms in a compound. It's a ratio, yeah. So guys, let me show you how this works. Some of you don't know me. I'm a left-handed guy. My handwriting is bordering on unreadable. But as bad as my handwriting is, wait until I start drawing. It gets worse. So guys, you may want to try to draw this with me, but do better than I do, okay? So this is the way they figure out empirical formulas. There's a couple ways they do this, but this is one way. So what they do is this. They have no, that's not a good word. This won't let me, oh, it does now. It let me erase. Okay, so they have let's just do this. They have a heating vessel. They have a place where they can add heat to substances. It's an oven. Should we just call it an oven? Good heavens. It's an oven. Okay, but guys, the trick here is this is an oven that can turn metals into gases. It's pretty hot. Yeah, then what happens, and that's a tube, okay, that's hollow. Can you see that it's hollow? Oh, good. And then, guys, what happens is they take this tube and they pass it through a series of what are called scrubbers. I know you guys have struggled with this, so let me help you out. You know when you buy a new pair of shoes and they have that little white packet in there and your first instinct is to grab that white packet and eat it? And then, thank the Lord, it says don't eat, saving you from that natural instinct to want to eat that packet. You know what I'm talking about, right? Okay. Well, guys, do you know what's inside that packet? It actually won't kill you. It's a silica gel. And that silica gel is what is called a desiccant. It actually sucks water out of the air. So while your Nikes are on their way over from China on a big old ship in the middle of the ocean, they don't get damp and rot. You guys understand that? So little insider trick here. If you ever throw your phone in the toilet, you know the trick about put it in a bag of rice? Actually don't. Here's what you do. Go to the mall and go to the purse store. I never go to the mall. It scares me. But you need to find a store that sells purses, because every purse that comes over is made in China and it's got one of those packages in it. Ask them for a bag of them, because they've got a ton of them in the back, and huck your phone in that bag, because those desiccants will suck the water out of your phone, and many times it'll fix them. How about that? Huh? All right. So guys, but what I'm trying to get across to you is those little packages actually contain a substance that sucks in water. Well, guys, it turns out that there are substances that can also suck in atoms, carbon, hydrogen, oxygen, for example. And when we use them in that mode, we call them scrubbers. So this is the way it works if you want to figure out what's in a substance. You take that substance, C6H12O6. What is that? It's a sugar. You take this sugar and you put it in this oven and you heat it up so hot that it not only turns into a gas, but it fall apart into carbon, hydrogen, and oxygen. Then you take that gas and you pass it through a series of scrubbers. And you put something in here that scrubs for carbon, you put something in here that scrubs for hydrogen, and you put something in here that scrubs for oxygen. And then what happens is as this gas travels through the scrubbers, the carbon sticks here, the hydrogen sticks here, the oxygen sticks here. What comes out the tailpipe? Nothing. If you do this properly, you will have no exhaust because you've scrubbed out all the elements. Now the question is, you've got to figure out how much carbon, hydrogen, and oxygen you've collected. How do you do that? Weigh them before and weigh them after. How do you figure out the mass of the carbon? Subtract, right? But then, guys, you've got to take that data and convert it into moles. You get the idea? And when you convert it into moles, does this start to sound familiar? And then when you divide by the smallest number of moles, remember that from the problem-solving process, what ratio will you get for this compound? 1 to 2 to 1. Now, guys, what about this? What if we take C11H22O11 and we pass that through the scrubbers? What ratio will we get? 1 to 2 to 1. What if we go C5H10O5? What ratio will we get? The same. That's why empirical formulas are the simplest formulas, because guys, it doesn't matter what sugar you pass through this system, you'll get the same ratio, meaning they have the same empirical formulas. Does that make better sense? Okay, now guys, and I told my class about this last year, so we've got 1 carbon, 2 hydrogens, 1 oxygen. 1 carbon, 2 hydrogens, 1 oxygen. So we've got carbon and water, which we call carbohydrate. That's why all sugars are carbohydrates, because carbohydrate tells you the empirical formulas for sugars because they can all be reduced to 1 carbon, 2 hydrogens, 1 oxygen. Yeah. So now, guys, some of you, your heads are going, wait, I know enough about sugars to know that they aren't all 1 to 2 to 1. The reason is because all sugars start as a long chain of carbon with water molecules attached to them. But sometimes those carbon chains loop around and make a circle. And when they do, they lose a water molecule. And so it actually throws off the ratio. But if you could bust the circle open and rehydrate them, they'll all come back to 1 to 2 to 1. You get the idea? Okay, so that is the story behind empirical formulas. But now, guys, we've got a problem that we need to solve. So, do you get this idea that it doesn't matter what sugar you put through there, you're going to get the same empirical formula? So then the question becomes, once we figure out it's a sugar, how do we figure out which sugar it is? Do you see the problem? You don't know the answer to that. We didn't learn that last year. So guys, we're going to build up to that, and we're going to answer that question right now. So guys, here we go. First of all, how do we solve empirical formula problems? And the answers are these. Write them down if you don't remember. So if you're given masses, and this is what Mark was talking about, you subtract the two numbers and it tells you the mass of the atoms that were collected. If you're just given the masses, you can assume that you started with a 100-gram sample and you can convert those masses or those percentages straight to masses. I said that backwards. If you're given percentages rather than masses, assume a 100-gram sample, and then your percentages can be used as masses. Then, guys, you're going to convert those masses to moles. Then you're going to find the whole number ratio by dividing by the smallest number of moles. Is that, you come and remember that? Okay. The masses? Just use them. Yeah. So, guys, let's try this. Ethylene glycol Do you guys know what that is? It's actually it's a derivative of an alcohol. It's actually the active ingredient, if you will, in antifreeze. So when you buy antifreeze, 100% ethylene glycol, which you can't buy, is actually pure antifreeze. They usually water it down. It's not actually an alcohol, though. It's actually closer to a sugar, which is why this stuff is really dangerous in your garage, because it's actually really sweet. And if you spill it, your pets will eat it and die. It turns out that about 5 or 10 years ago, there were French winemakers that were actually putting ethylene glycol into some of their wines in order to enhance the sweetness of it, and people were getting sick, and that was bad. So, although it turns out, you want to know this is funny, I learned this in college. The antidote for antifreeze poisoning is actually beer. So it's what's called competitive inhibition, because there are molecules in your body that grab a hold of this ethylene glycol and they can't let go, and it poisons you and dies. So if you ever drink antifreeze, what you want to do is then drink beer, because it turns out the alcohol molecules in beer are much the same shape as the ethylene glycol molecules, and these same molecules in your body grab a hold of the alcohol molecules, and everyone that grabs a hold of an alcohol can't grab a hold of an ethylene glycol, and therefore you don't get poisoned, and then later your body can let go of the alcohol molecules and it all just sort of goes away. So if your dog ever eats a big old cup of antifreeze, give him a beer. He'll be fine. No, actually he'll probably still die, but we tried. So guys, ethylene glycol is made of carbon, hydrogen, and oxygen. Notice the percentages. We are going to figure out the empirical formula. You know steps, but I'm going to go through them with you because you've done this before. So here we go. And guys, do you remember how I structured these problems when I taught them to you last year? Do them in columns. So it goes like this. 38.7 grams of carbon, 9.7 grams of hydrogen, and then finally 51.6 grams of oxygen. Now guys, I want to hit on an important subtle point here. We're going to convert these to moles, right? So carbon has a mass of 12.01 and change. What mass are we going to use to convert to moles? 12.0. Notice the rule, 3 significant digits here, 3 significant digits here. 12.0 is 1 mole of carbon. Now guys, we got to talk about hydrogen. I can't even ask it as a question, you won't remember. Do you remember that hydrogen is diatomic? Hydrogen bonds to other hydrogens and it makes H2. So which one are we talking about? Is this H or H2? And the answer is it's individual hydrogens. The question is, how do we know to use the mass of hydrogen, which is 1, and not the mass of H2, which is 2? And the answer is this. Where did that hydrogen come from? Ethylene glycol. It came from another compound. So this hydrogen was in another compound. When does hydrogen bond to itself? When it's alone. So because it came from another compound, we will treat it as an individual hydrogen, and therefore the mass is 1. And then oxygen, 30, now I used the wrong one there, 16, for the same reason. 16.0 grams is 1 mole. All right, 38.37 divided by 12. So 3.23 moles, 9 point. Did I do it wrong? I'm just making stuff up. See, hey, the answer is right though, isn't it? Oh, bless my heart. 9.7 divided, oh, hey, I can do 9.7 divided by 1. I can do that in my head. What? And then Okay. So guys, now we know the molar ratio. It's 3.2-ish to 9.7 to 3.2. But of course, we can't use that as a chemical formula because you can't have fractions of atoms in a molecule. So again, how do we convert this to whole numbers? Divide by the smallest number of moles, which is 3.23, 3.23, 3.23, and we get 1, approximately 3, and 1. So now we've got 1 carbon, 3 hydrogens, 1 oxygen, and that is the empirical formula for ethylene glycol. Now, carbon hydronium, no. Now, guys, we've got an interesting question. Is this ethylene glycol? Maybe. There are times when the empirical and molecular formula are the same. But we do know this. What will the actual formula for ethylene glycol be relative to this? It'll be a multiple of it. It will maintain that 1 to 3 to 1 ratio. Does that make sense? Okay, so now, guys, that's the leap that we need to take. We're going to now answer that question by talking about what are called molecular formulas. So what is a molecular formula? Okay. So guys, the molecular formula represents the compound as it actually exists. From knowing the empirical formula, we know the ratio. But we want to know what ethylene glycol actually is. So how do we do that? Well, guys, in order to do that, we need to figure out how to take molecular formulas and turn them in, empirical formulas and turn them into molecular formulas. Here's the process. In order to do this, we have got to know the molecular weight of the compound. How do you figure that out? Through experimentation. You take these compounds, you react them with other compounds. By collecting and weighing the products and balancing equations, you can work it backwards and figure out the formula mass of the substance. We will be doing that in lab in about a month. Now, no?
Not trying to sound stupid or anything, can you not just add up the atomic numbers of the elements?
You don't know what to add up. You
Like,
know.
for instance, if you have like carbonate or something, you can't just take the 12,
You,
101.
Sure, but you don't know how many.
Oh.
And that's the problem. You don't know how many of them there are. Yeah, absolutely. And that's what this is going to let us do. Is that a good sentence? Yeah. So guys, this then is the process. You are going to calculate what we call an empirical mass. Then you're going to divide the molecular mass by the empirical mass. And again, empirical masses are found through carrying out reactions. And then you're going to create a multiplier, which you will then apply to the empirical formula to get the molecular formula. That doesn't make any sense at all, does it? I'll show you. You can write it down if you want, but when I show you, you're going to go, oh, I get it. It's not hard. Oh, man. My super duper smartboard pen already cracked. You guys all caught up with me? So guys, what does this look like? Well, are you okay? You guys are very dutiful note takers. That might not have been a compliment. You guys know how this goes down in college, right?
Scribble down what you can.
Oh no. So yes, but most college professors are not comfortable with PowerPoint and things like that, so they still teach some of them on chalkboards. Many of them have moved up to whiteboards. But guys, it is, the first time you see this, your mind kind of just goes, boop. Because what happens is, you know, like freshman chemistry, BYU, University of Utah, they're taught in movie theaters. Do you know that? The seating is like a movie theater. Freshman chemistry at BYU, there's about 600 students in each class. And when you walk into the class, they call them snake pits. It's literally theater seating, and the professor's down front. And he's not teaching you, he's teaching the board. Typically, you just see, or she, you just see their back for the entire day as they scribble stuff on the board. But what happens is they scribble, and when they finally run out of board, you're like, thank goodness, now I can catch up. But what they do is they actually take these boards and they throw them in the air, and they're on pulleys, and they lift up in the air, and those boards are up in the air, and there's boards behind it, and they just keep writing. It's awesome. You're going to love it. Okay, so you guys all caught up now? So guys, this is how this goes down. Don't write this down, but think through it with me. It says, what is ethylene glycol? If it has a formula or a molecular mass of 62.1 grams per mole. So if you have a mole of ethylene glycol, it weighs about 62 grams. So what is the formula for this stuff? Well, guys, this is how you figure that out. From the previous problem, we figured out that the empirical formula for ethylene glycol was CH3O. We are now going to come up with what we call an empirical mass. This is 12, this is 3, this is 16. We add those up and it's 31. So this is about 31 grams per mole.
Wait, you don't need to do 3 times 3?
I did. Hydrogen is 1 times 3. Yeah. No. Hydrogen weighs 1 and there's 3 of them, so that is 3. Yeah. Now guys, did you notice the way that I wrote the units for this number? Grams, moles, -1. Mathematically, what does it mean to have a -1 exponent? It means in the denominator. Okay? So you're going to find that many times in our book, we will not write grams per mole like this. This is the same because a -1 exponent simply pushes it into the denominator. Does that make sense? Okay. So bottom line is we now know how much an empirical unit of ethylene glycol weighs, 31 grams. Now we're going to come up with a funny little equation that says the molecular mass divided by the empirical mass gives us a multiplier. Now guys, the molecular mass we were given, 62.1 grams per mole. The empirical mass we figured out, 31, let's be consistent, 31 grams per mole. When we divide those, we get 2. So what does that tell us about the actual formula for ethylene glycol? It's twice the empirical formula. So that means ethylene glycol is actually C2H6O2. Does that make sense? Is that okay? All right. So guys, we've got one more thing to do today and we're done. And it's a doozy. Do you have questions or can I go on? You good? Yeah.
Quick question.
Mm-hmm.
So, any of the homework problems, they will give us the molecular.
Yeah.
You don't expect us to solve it.
Well, you could. I mean, if it, well, no, you couldn't. That'd be stupid. Yeah, no. In lab later on, you'll find it, but no, they'll give it to you. Yeah. Okay. So guys, this is how we're going to wrap up the day. Don't take notes. It's not going to do you any good. How's that for fatalistic? Okay, so guys, in class back in February, once you figured out the mole and once you figured out how to write balanced equations, then we brought those two things together and we started talking about stoichiometry. Remember that? The math of chemical reactions. And we talked about these things called mass-mass problems. Now, 3.6 in your book is quantitative information in equation, and it talks about mass-mass problems. So, then it gets into the idea of limiting reactants. And do you guys remember the idea behind limiting reactants? Limiting reactants are the reactant that you run out of first if you burn a match. Thank goodness the limiting reactant is the match, because otherwise if it was the oxygen, we'd all die, right? So guys, the limiting reactant, we call the limiting reactant because when it's gone, the reaction is over. It limits the extent of the reaction. And then guys, we talked about this idea that to calculate limiting reactants, we took the mass and converted to moles. Then we divided by the coefficients from the balanced equation, and then whichever number was smallest was the limiting reactant. You remember that? Okay, here we go. Then guys, we talked about an idea called theoretical yield. And we talked about the idea that a reaction can create product. And the amount of product that a reaction can create is limited by the amount of limiting reactant. And by combining this idea with the idea of mass-mass problems, we then figured out how much product a reaction could produce through some mathematical steps. Okay, so with all of that said, here you go. Write this down. 2C6H12. That reacts with oxygen, 5 of them, and it produces 2 H2C6H8O4s and 2 waters. You guys were hoping this was going to be a combustion reaction, right? It ain't. Is that big enough to read? That's okay, right? So when I switched to this new board, did you notice that it's wider than it is? You know, it's not square, it's rectangular. And so when I reformatted my slides to this wider format, it made all the type smaller. Is this big enough to read? Is it like pushing the limits like you're, ooh, that's, I can't quite, or is it comfortable? Yeah, okay. Guys, if you ever find this stuff is just getting too small, please let me know. Okay, so here's the deal. Assume that you have 25 grams of cyclohexane and 25 grams of oxygen. Okay, so guys, let's talk. You have no idea what cyclohexane is, right? So now let's have a conversation. One of the things that's going to be challenging for you at first in this class is that you're not going to be spoon-fed information. Guys, on the AP test, they would not have qualms at all about giving you information about compounds that you've never even heard of. Because guess what? You can figure this out. What's this? Water. What's this? Oxygen. So which one's the cyclohexane? Well, it's got to be one or the other, right? But if we look into this, we can then dig a little bit deeper, and it says assume that you use 25 grams of cyclohexane. And if you're using it, what do you think it probably is, a reactant or a product? Reactant, so it's going to be the one on the left. See? So now we know that the cyclohexane is this guy. Now, let's read on. 25 grams of cyclohexane, 25 grams of oxygen. Here are the questions I want you to answer. What's the limiting reactant? What is the theoretical yield for adipic acid? And if you receive 33.5 grams of adipic acid, what's your percent yield? Because you have 12 minutes to solve this problem. And then we're going to do it together and call it a day. Actually, that's not true. Then we're going to do Pride, where we are going to go over a little bit of the student handbook really fast. And then we're going to get out of here so I can eat lunch and then go for a bike ride back to school. You haven't noticed the smile. I have fourth period prep. Don't tell anyone. Take it away from me. Frankly, should I say this out loud? Yeah, I'm going to. That's the beauty of teaching at a school where none of the coaches teach here. Because it used to be that all the coaches got the fourth period preps to work with their athletes, but now that none of our teachers coach, they're very good. And actually, what I said isn't completely true. We do have a couple coaches who are teachers. Not many, though. which would potentially make me a hypocrite other than that I did coach here for 12 years. Ballroom. No, I'm kidding. Volleyball. I played volleyball in college, and then I coached volleyball here for 12 years. Huh. There's no such thing. Yeah, Title IX won't allow guys volleyball, because if we pick up a guy sport, we have to pick up a girl sport, and they don't want to pay for it. They actually talked about lacrosse, but it didn't happen, which would have been... Well, it does, because there's guys wrestling but not girls wrestling, and so it does in fact balance out. Right. Yeah. A little disappointed you guys didn't think I could be the ballroom teacher. You can see it. So guys, again, 3 questions. And actually, I know you're working, but let me just tell you right now, guys, you're going to get really accustomed to questions like this, because this is what all the questions on the AP test look like in the free response. They're multi-part questions. And what you're going to find out is that these questions will always be written so that in order to answer question number 2, you have to get question number 1. And in order to answer 3, you have to get 2. They'll always build on themselves. So, and this one does as well. The nice part on the AP test is if you get question 1 wrong, but use that wrong information to get question number 2, they'll give you the credit for question 2, even though technically it's incorrect. I won't do that for you on your test, though. I'll just mark them all wrong. Well, it's because I want you to rewrite them. Oh, guys, I forgot. We didn't finish the conversation about testing and grades in here. Remember how we stopped at the end of Monday? We'll pick it up later. Because we're going to go for about 5 more minutes. Dylan, it's got to be nice to be able to write again. So guys, we're going to go for 2 more minutes. So guys, I don't want to rob from you the opportunity to get an answer, but I also want to have time to go through this with you. Can we try it together? Is that okay? So I need some feedback here. How low can I go on this screen before it becomes so low that you can't read it? Like, can I go clear to the bottom, or is that just pushing it? You guys are good? But, I mean, is it like how... Okay, so, but it probably doesn't get any worse if I go further down. Tell you what, I'm going to try this, and if you tell me it's just getting hard at some point, I'll just remember that. So let's try this. So guys, again, notice that these questions are asked in an order. And if you were to try to answer just question number 3, guess what you'd have to do to get to that answer? 1 and 2. You can't come up with the answer about theoretical yield, or I'm sorry, about percent yield without knowing about the theoretical yield. And you can't know the theoretical yield without knowing how much of that product you can make, which is based upon the limiting reactant. So we've got to solve it in this order. So limiting reactant first, and it goes like this. We've got 25 grams of each. So we have 25 grams of C6H12. We have 25 grams of oxygen, and we need to convert both of those to moles. Now, guys, just help me. Oh, wait, what is the mass? Is it 84? The mass of, okay. Oh, you're right, because this, yeah, so 84.1 grams is 1 mole of C6H12. Then, guys, why do we use O2 and not O for oxygen? It's by itself. It is floating around in the air, And so it's bonded to another oxygen. So it really is 32 grams is 1 mole of O2. Can you help me out here? What does that divide out to? Top one. 297 moles. And what about the bottom? 0.781 moles. Okay, so now guys, this is where people tend to make a common, how'd that get there? This is where people tend to make a mistake. Oh, it's just there. All right, well, let's do this, do this. Okay, so at this point, what I'll see a lot of people do is they'll divide by the smallest number of moles. What are they thinking? Empirical formula. But guys, we're trying to figure out the limiting reactant. And so in order to do that, what we've got to do is respect the fact that these don't react in a 1-to-1 ratio. See, what happens is every 2 cyclohexanes will combine with 5 oxygens. So now we need to do this math. What does this one divide out to? 4,9? How about the top one or the bottom one? 0.156. Okay. So guys, at that point, we are now ready to identify the limiting reactant. And which one is it? The top or the bottom? Top, the smallest number. Guys, understand though that just doing the math is not the answer to the question. You need to actually identify C6H12 is the limiting reactant. Without doing that, you have not properly answered the question. So now, guys, let's pause and ask questions. Go ahead, ladies. You guys okay? So, please, Valeria. Yeah, so it's these numbers right here. Yeah, it's the coefficients, because these coefficients tell you the ratios in which they balance, or which they react. I'm so glad you asked. Are we good? Concerns? Mark, you okay? Are we good? Okay. So now, guys, we're ready to answer. Oh, go ahead. On the, here's the, and it's an interesting question, because what you need to get good at is answering the questions without saying too much. So if the question says, what is the limiting reactant? I think what I wrote's not inappropriate, but just writing cyclohexane wouldn't be wrong. Would be okay. Yeah, okay. So now, guys, what do we do with this? Well, now we know which one of these substances is going to limit how much adipic acid we can make. So let's have the conversation. Which one is the adipic acid? It's the only one we haven't identified. We know that this is water and that's oxygen. We figured out earlier that this is cyclohexane, so it's got to be that. So where do we start? Well, guys, we start with the mass of our limiting reactant. Is this just too low? Can I go down here? Is that okay? So, guys, we go 25 grams of our cyclohexane. And what we want to know is how many grams, and I'm just going to call it AA, how many grams of adipic acid. Now, in order to figure that out, we need to do some dimensional analysis. So we already know 84.1 grams is 1 mole of C6H12. What is our next step in figuring out our theoretical yield? The mole-to-mole ratio. So we need to know moles of C6H12 as compared to moles of adipic acid, which at this point we should write down H2C6H8O4. And guys, that ratio, hey, this is handy, is 2 to 2. Then, guys, we go 1 mole. Wow, this is really wiggly. Huh. Okay, so 1 mole of H2C6H8O4. How many grams is that? Did anyone get it? 146? Good enough for me. All right, so then, guys, we do the math. Did any of you get the math? 43 point what? 5? So, guys, I haven't done the math, but I trust you. And maybe we should confirm as a group. Does this seem like reasonable numbers? Okay. So now what do we know? Well, guys, we know that if we dump in 25 grams of cyclohexane and burn it up with 25 grams of oxygen, there's going to be oxygen left over, and we're going to make 43.5 grams of adipic acid. Now, what if we collect 33.5 grams? Is that good or bad? And that's what percent yield is all about. And guys, we would obviously solve this by continuing down, but I'll do it up in the corner where I have space. And it goes like this. Percent yield is equal to the actual yield divided by the theoretical yield times 100 to make it a percentage. Our actual yield is 33.5 grams. Our theoretical yield, which came from the calculation, is 43.5 grams, and we multiply that by 100. Who did the math? 77? 77%. So you lost 23% of your adipic acid. And there you have it. The percent yield is the 77%. The percent error would be...
So if they said, what is the percent error, then we would give it 20.
Yeah, but remember that percent error is actual minus theoretical divided by theoretical. And it's that subtraction that gives you the other part of the whole. So guys, how we doing? You okay? All right. We just did chapter 3. This then is your homework. Out of the end of chapter 3, these are the end of chapter questions. You're going to do 3, 5, 7, 14, 19, 25, 37, 45A, 49, 57, 63, 79. Now, guys, understand that this is posted online, so if you don't want to write it down, you don't necessarily need to. This is all from chapter 3. Yep. I'll give you a second to write it down.
Section 3, questions 3 and 5.
Chapter 3.
This is Knappenberger. It's 45A. You don't have to do the other multiple choice options.
No.
That's what I'm
Just that one. Yep. So guys, we're not done there though. There's more. I'm verifying this date. So I see you Friday, so I'll see you again Tuesday. Okay. So guys, in addition to that, you've got 2 other things you're going to do. You are going to outline chapter 4. But this is not due on Friday, it's due on Tuesday. We are going to start chapter 4 on Friday, but asking you to do all this homework and a chapter outline was sort of flirting with child abuse. So I figured we'd give you the weekend. But then, guys, this you do need to bring next time. I want you to summarize, and some of you have already done this because you figured out that there were some amazing patterns to the solubility table that you had to know for the quiz. So if you, well, on page 121, table 4.1, that's the solubility table, I want you to summarize it. And the kind of things that we're looking for are things like all the halogens, nitrates, and acetates dissolve in water. It's actually pretty close to true. All of the alkali metal salts dissolve in water. You're looking for broad generalizations, things that you'll remember throughout the year. So you're going to do that. And that'll do you. So guys, hold on. This is going to go away for a second.